Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 11th episode of my tutorial series on Z80 assembly language development, targeting the Sinclair ZX Spectrum to learn how to program a simple system, starting at the very lowest level. If you haven't seen the earlier episodes, I strongly encourage you to go back to my channel, and don't forget to subscribe and click the bell to be notified when the next episode comes out, and start this playlist from the beginning. So far in this series, we have learned the basics of assembly language and how each instruction for the Z80 works. Last time, we started getting more into the specifics of the ZX Spectrum, starting with the ROM that was designed to provide the Sinclair Basic Interpreter. We have seen how to use the ROM to print out text to the screen, but what about graphics? You may be familiar with the graphics commands in Sinclair Basic that let you draw lines, circles, and even individual pixels. But if you need to do anything more complicated, it is very slow. If you are programming an assembly, you have access to multiple efficient ways of getting graphics on the screen, and this lesson will show you the fundamentals of how to do each of them. The simplest way to make graphics is, as one would expect, also the crudest. On the Spectrum keyboard, the number keys 1 through 8 each have a little 2x2 graphical pattern printed in the upper right corner. These can be typed to the screen while Basic is in graphics mode, which you can enter by holding down Cap Shift and pressing 9, which you can see has the word graphics printed above it. The cursor changes to G, and if you type any of the numbers 1 through 8, the graphic character on those keys will appear on the screen. If you hold down Cap Shift while pressing the number, the inverse character is printed. Because these characters are still 8x8 bitmaps, just like the rest of the character set, the quasi-pixels in these 2x2 patterns are actually 4x4 pixels of solid colors, and use the current paper and ink colors. So these 4 chunky quasi-pixels can be any arrangement of 2 colors with the same brightness. On startup, Sinclair Basic has brightness set to low, the paper color set to white, which means it's actually gray because of the low brightness, and the ink set to black, which is always actually black, regardless of the brightness. You can use the basic tokens for bright, paper, and ink to control these colors as well. But as we saw in the last video, all of this can be done quite easily in assembly as well. Of course, in assembly, we don't have to worry about shifting to get the characters we want. We can just print out the codes for them, just as you would in Basic using the CHR function. But we can use constants to make it more readable. The graphics characters have the hex codes 80 through 8F, totaling 16, meaning that there are twice the number of graphics characters than you see on the keys. Hex 81 through 87 match up with number keys 1 through 7, but the rest are just inverses of those 7, and then all paper at hex 80 and all ink at hex 8F, which gives you all the different permutations of 2x2 bitmaps. So printing hex 83 using the RST10 routine will print the graphics characters on the 3 key, which is all ink on the top half and all paper on the bottom half. You can build graphics using these characters, but they are mainly only useful for drawing thick lines and boxes around other characters, unless you only need 1/16 of the Spectrum screen resolution. Of course, this was rarely done for any games, as there are better ways of leveraging both the ROM software and the full video resolution. That would be User-Defined Graphics, or UDG for short. The Spectrum character set features 21 codes that are repeats of the letters A through U by default. Rather than having the bitmaps for these glyphs in ROM, these 21 get their bitmaps from the very end of RAM, starting at hex address FF58. At startup, the bitmaps for letters A through U are copied from ROM to this part of RAM, but then you can overwrite them at any time to make up 21 8x8 bitmap characters of your own design. You can define these with a series of poke commands in Basic, in conjunction with the USR function to get the starting address for the UDG glyph you want to overwrite. Here we can see how we make the UDG O glyph turn into an 8 by just changing line 3. But this is a bit cumbersome and not exactly fast. While in assembly, we can do this much more efficiently by quickly loading bitmap data to addresses that can be defined as constants. And then we can print them using constants for their character codes, just as we did with the fixed graphics characters. but this time using the hex codes 90 through A4. And then, once the character is printed, the glyph can be changed and printed again, giving you a new 8x8 bitmap while not changing the earlier one that was printed using the same code. We can see that happen here in this short example, where we print out UDG O twice, once using the original glyph and then changing it to 8 like we did in BASIC. Now we have the ability to use constants for the character code and the bitmap address, and even use binary to define a line of pixels. Of course, most of the time, a UDG character would be used more than once on the screen, and the glyph not change quite so often. But you have the flexibility to use them how you want, and it makes it easy to combine higher resolution graphics with standard text, while still leaning on the ROM to handle all the rendering. But again, that's not what most programs do, and games in particular rarely use UDGs for graphics. It's even more efficient and flexible to just access screen memory directly. You can have a bitmap of arbitrary size and RAM, or loaded from tape, and write that directly to the screen memory. As we've seen before, screen memory is split into two sections, the bitmap and the attributes. The bitmap is just that, a representation of every pixel within the 256 by 192 display area. The border around that area is a single solid color, and we'll see how that works in another episode. The bitmap screen memory starts at hex address 4000, which is not just accessible to the Z80 CPU, but is also read by the Spectrum ULA while outputting the video signal. You might expect this bitmap data to be arranged in RAM in the order in which the ULA needs to read it, but you would be wrong. Instead, it is optimized to make it easier to manipulate the address while it is stored in a register, so that incrementing the low byte of the address increases the X position, and incrementing the high byte increases the Y position, but only within an 8-line span. This can be very confusing, so let's take a look at a better illustration. The X and Y coordinates of pixels each require 8-bit values, with the origin of the coordinates at the upper left corner of the display area. But these bits aren't in their natural order. To get the address of a pixel in screen RAM, the upper 3 bits of the high byte are fixed at 010, as the screen RAM begins at hex 4000. Then we have the 2 highest bits of the Y value, followed by the lowest 3 bits to complete the upper byte. Then the lower byte starts with the remaining 3 bits from the middle of the Y coordinate value, followed by the upper 5 bits of the X coordinate. We don't need to have the lower 3 bits of the X coordinate because each address is for a whole byte, meaning 8 pixels are encoded since pixels must be either ink or paint. If the bit is set, then it uses the ink color. Clear bits are the paper color, just as we saw for the UDG characters. Also, like UDG, the most significant bit in each byte of screen RAM is also for the leftmost pixel in an 8-pixel run on a single line. Now we can see that when we increment the low byte of the address, it will point to the next 8-pixel run on the current line. Of course, if the address is already referencing the end of a line, an increment will corrupt the address, jumping ahead to the beginning of a line that's 8 lines lower. That's an effect that will definitely be familiar for old Speccy users, as that's what they would see when loading graphics from a tape. Incrementing the upper byte alone will jump to the same position on the next line, as long as you are not on the last line of a character row. That is, as long as the pixel directly below will have the same attributes. Incrementing beyond that point will cause a jump of 64 lines, as you would overflow into the upper 2 bits of the Y coordinate. So as you can see, this layout was made to easily render graphics on a line-by-line basis, and within character rows, but not for easy calculation of big vectors that span a significant part of the screen. If you just need to address a specific pixel, it will require splitting up and shifting its coordinates to build the address you need to reference. Here we will define a routine that will set a pixel to the ink color at an XY coordinate defined by the B and C registers, respectively. Of course, X can be any 8-bit value, as the display area is 256 pixels wide. but Y must be less than 192 or the address will go outside the bitmap RAM. This code will do it, and as you can see, it is a bit involved, so let's bring back that illustration of the bitmap address format as a visual guide to what we're doing. First, we load B into A to get the X coordinate. We need to split this up into the upper 5 bits, which will go into the address, and the lower 3, which will determine which bit will be set at the calculated address. So first, we mask out those lower 3 with an and then save that in the D register for later. Then we load B into L, which is its final destination, but then it needs to be shifted 3 bits to the right to leave behind only those upper 5 bits that will be in the address. With X dispatched, we move on to breaking the Y coordinate into 3 pieces, so we start by loading it into A from the C register. We need the lower 3 bits of that at the low end of the H register, so again we do the AND with 7 and then an OR with hex 40 to get those fixed upper 3 bits of the address set as well. Then we load that into H and move on to the next part. We tackle the middle 3 this time, which we get by loading the Y coordinate back into A and then masking out those bits by ANDing with hex 38. We need to shift that 2 bits to the left to get that part all the way to the high end. Then OR it with the X coordinate bits we already have in the L register, which we then write back. We get that Y coordinate one more time, then AND out the upper 2 bits and shift them 3 bits to the right. We OR with the bits already in the H register to put them right where they belong in the middle. Now the address is complete, so we store the high byte back, making HL point to the 8-pixel run we're targeting. All that's left is to set the required bit in the byte at that address, so we'll need a loop to shift that into place. We initialize the loop by loading 0 into A, then setting the carry flag to have our moving bit start there. In each iteration, we rotate A to the right, which means the first time the set bit will move from the carry flag into the high bit of A. Then we decrement D and keep looping until we decrement past 0 and the sign flag is set. This means if D is 0 at the start of the loop, then that top bit will stay set. Otherwise, it will shift to the right by the number of bits specified by D, which could be up to 7, placing that set bit all the way at the low end. With the set bit in the correct position in A, we OR it with the byte in screen memory that HL is pointing to after our earlier calculation, and then store it right back with the desired bit finally set in screen RAM. Now we can return and keep calling this routine with different coordinates in B and C. You can make a very similar routine to clear a pixel, and all you'd have to do is just invert A after the loop and then AND it with the current value in screen RAM before writing it back. So you're only adding one instruction and changing the opcode of another. This is definitely not the most efficient way to populate the bitmap, but if you did just need to set a pixel here or there, this will work for any arbitrary coordinates. Generally, you need to have a better strategy for populating the bitmap, and make your code more customized to the task at hand. We'll see how to do that in later episodes. As we have seen so far, the bitmap memory is only concerned with whether pixels are paper or ink. The attribute memory determines what those paper and ink colors are going to be. As we've learned already, the spectrum doesn't have attributes for individual pixels, but rather for 8x8 pixel tiles, which line up with character positions when using basic text. So for each pixel, we must determine its tile coordinates by dividing the pixel coordinates by 8 and throwing out the remainders. Then to calculate the address in attribute RAM, we have it a bit easier than with the bitmap RAM. Attributes start at hex address 5800, and the tile attributes are in the more intuitive order of each row from left to right for all 32 tiles in the row, then continuing down row by row until you get to row 23 at the bottom. This means you just have to multiply the tile Y coordinate by 32, and then add it to hex 5800 and the tile X coordinate. The attributes at that address apply to all 64 pixels in its corresponding tile, and those attributes all fit into a single byte. The most significant bit will enable flashing when set. This means that the paper and ink colors will continually switch with each other. This is not used very often, unless you have some sort of cursor or other prompt. The next bit is for brightness, which will make both the ink and paper the bright versions of their colors when set. Then we have 3 bits each for the paper and ink color indexes, which means that we have 8 different colors to choose from, but 2 brightness levels for each of them, and both colors in the tile need to have the same brightness. This might lead one to say that the spectrum has 16 possible colors, but that's not quite correct. The brightness attribute affects all colors except for black, which is always just black. If brightness is enabled, we get full intensity blue, red, magenta, green, cyan, yellow, and white for colors 1 through 7, which gives the spectrum its characteristic brash primary color look. With brightness off, we get slightly muted versions of these colors, with white becoming the neutral gray that we recognize as the default paper color in Sinclair Basic. Throughout this series, we'll show different ways of organizing graphics to avoid the other hallmark of Spectrum graphics, attribute clash, where the limitations of this attribute scheme become all too apparent. For now, let's go and review all these methods of generating graphics, which we can do with our example program. We'll be making graphics with the fixed graphic characters, UDGs, and directly manipulate the bitmap by both loading data from another part of memory and setting pixels programmatically. At runtime, we'll be able to see this beautiful picture, but first, let's go to the code. As usual, we start our assembly code file by specifying the 48K spectrum as our target machine, and beginning our code at hex 8000. Before we get there, we have some constants to define, starting with the address for the ROM routine that will clear the whole display area. Then we have some character codes, starting with control codes, and then the fixed graphics characters. Each of them are identified by the letter that they print by default. After those, we get to the UDG characters, and we define constants for the first 10, as that's all we're going to use in this example. Then finally, we have one last control code at the bottom, stop, which we will use in an unusual way, as you will see soon. With all the constants defined, we move on to the data, starting with the UDG characters we want to print. We are using UDGs to print the italicized Slithy and the Slithy Games logo. For each character, we need 8 bytes to make the 8x8 bitmap. Our first UDG will be for the top row of characters, which will render the upper halves of the taller letters, starting with the stem for the L and the dot for the I. To make it easier to visualize the bitmaps, we can define them with binary literals, which start with the %sign. We continue with that for all 10 UDGs, then define a constant that will let the assembler calculate the size of the UDG bitmap data. The $sign in this context means the current address, rather than a hex literal, as it's not immediately followed by any numbers or letters. We subtract from that the starting address of the first UDG bitmap, and now we know how much data to write to the UDG RAM. Then we have our banner, which is just a long string of character codes to print. As you can see, there is a mix of control codes, numerical arguments, string literals, UDG codes, and fixed graphics codes. You can see that we start with setting up our attributes for the first printable character. We turn on brightness with the bright code, followed by 1. Printing that 1 will be interpreted as an argument, as the previous code printed was bright, which requires one argument, either 0 or 1. All of the other attribute control codes require arguments as well, so we follow flash with 0 to turn off flashing, paper 7 to make the background white, and ink 4 to make the foreground green. Now that the attributes are set, we can print out actual characters, starting with a space, and then the first 3 UDG characters and a couple more spaces. So what's in those first 3 UDGs? Well, we took a look at the first one in the code, but to better illustrate, let's look at the full matrix of UDGs that we're going to print. Here we can see all of the UDG tiles that we needed to find to make the stylized version of the word Slithy, starting with the top row where we have 3 custom characters. The first one, as we saw in the code, has the top of the L and half of the dot over the I. The hash lines are there to better show where the tile divisions are, but for more clarity, let's add the constants we are using in the code. Now we can see all 10 UDG characters identified, and that we need a row of 5 tiles on the second line, then 2 more on the third line. Now let's go back to the banner data and see how we put that in. So after that first row of UDGs and a couple of spaces, we start by setting up some new attributes. We turn brightness off, then change the paper color to red, identified by number 2. Then we print out a whole bunch of spaces to make a big slab of solid dark red. Then an enter will take us to the next line. We reset the attributes by turning brightness back on and making the paper white again. Now we have that middle row of 5 UDGs, followed by a single space, and then we change the attributes again to turn off brightness and make the paper red. But this time we are also making the ink white. Since brightness is off, this white ink will actually be gray. We print out another single space, which will just be solid red, and then a long string of fixed graphics characters, ending with another enter to finish the line. It's difficult to visualize what this is doing in the code, so let's take a closer look at the graphics we are trying to generate. As you can see, we are using the fixed graphics characters to make a big banner that says Presents, which will require 3 rows of 21 characters each. A spreadsheet like this is a good way to plan some blocky graphics, and then use borders to highlight the individual tiles. Then below that, we can list out the graphics character index values for each tile so that we know what to print out. For simplicity, we just use the lower nibble of the code to identify the character. And since we defined constants for those codes anyway, we don't need to remember that the upper nibble for each code is 8. Back in the code, we can see that we just copied that matrix of index values from the spreadsheet and inserted the GFX underscore prefix before each of them and put commas between them. We print and enter after the first row, then reset the attributes to green on white to print out the last row of UDGs with some spaces to pad them out. Then we reset the attributes again for gray on red to print the second row of graphics characters from the spreadsheet, and another enter to go to the next line. For this line, we want to start with black ink on white paper, so we turn on brightness and set the paper to white as before, but then print ink 0 to make the text black. We then print out games followed by a space, which will go directly under the slithy we rendered in UDGs. Then go back to gray and red one more time to print the last row for Presents. After another enter, we print the last line in the banner, which is all spaces, going from white to dark red paper to give us a little bottom margin. Then we finally have a stop code, which will let our program know that there is no more text in the string to print. After the banner string, we see something new for this series, a pair of ink bin directives. This allows us to include binary files in line with our assembly code. This is an easy way to define a large section of binary data without having to clutter our assembly code with several kilobytes of data declarations. This is where we will have a partial bitmap and a partial attribute section for doing some externally defined graphics. Doing this kind of include lets us use a more generic image creation program, and in this case we started with GIMP, which is a multi-platform free and open source alternative to software like Adobe Photoshop. GIMP lets you set up a custom indexed palette for your image, so for the spectrum we want to mimic what the attributes allow. This means a 16 color palette that's in the same order as the spectrum palette, with colors 0 through 7 being the same as the colors that the spectrum will display when brightness is off, from black to gray. Then colors 8 through 15 are the same colors repeated, but with brightness on, so that color 15 is white. So the color index in the image can be easily converted into spectrum attributes, with the lower 3 bits for the ink or paper, and then setting the brightness bit for colors in the upper half. You'll notice here that color 8 is not quite black, but more of a dark gray. This is to help differentiate black with brightness on from black with brightness off, which is actually rendered as black here with color index 0. Of course, a spectrum bitmap must have consistent attributes for each 8x8 tile, with only 2 colors of the same brightness, and having this bright black helps us to make sure that the correct black is being used before we do the conversion process. If you look carefully, you will see that this image does have consistent attributes, with the bright black patches helping to highlight where those tile boundaries are. With this image complete, we can have GIMP export it as an indexed PNG file to make it ready for processing. An indexed PNG will use an internal palette, and GIMP will keep the same color index ordering as the original GIMP format file. To take that PNG and turn it into the binaries that we are going to load into memory, we need to convert it to the Spectrum's bitmap and attribute formats. This Python script will do just that. It uses the standard pillow library for image processing, which we import in the first line. If you aren't familiar with Python, don't worry. This isn't a Python tutorial, so I won't be going through this code in detail. But assuming you have experience in some sort of high-level language, it should be pretty easy to follow. First, we define a function that converts a normally ordered bitmap line number to a Spectrum bitmap line position in screen RAM by splitting it up into the 3 parts we saw earlier and rearranging the bits. We keep the upper 2 bits in place, but switch around the remaining bits by swapping the position of the lowest 3 bits with the 3 bits in the middle. Even if you are an experienced Python developer, it's fairly unlikely that you have written code like this, but we are effectively using Python as a cross-development environment for the Spectrum. Then we can see that this script expects that it will have at least one command line argument, a PNG file name. Then there are 2 optional arguments, with the second being a starting line on the screen where this bitmap will be rendered, and a possible third that defines a starting pixel column for the bitmap on the screen. If these coordinates are not specified, the default values will both be 0, meaning that the default starting pixel will be in the upper left corner of the display area. In the case of the image we created in GIMP, it is 256 pixels wide, so it will need to start at column 0 to take up the full width of the display area. However, we don't want to start it at the top, but rather below the tiles we are printing out, so we will be setting a non-zero starting line. Then we open the image using Pillow's image.open method and passing in the file name from the command line. The return value is an object with several attributes that we can check to see if this file is indeed an indexed PNG that we can process. First, the format attribute must be the string PNG. Then we check the mode attribute for the value P, which indicates 8-bit indexing. Next, we check the dimensions of the image to make sure that it will fit within the 256 by 192 pixel display area given the starting line and column. Finally, we make sure that the palette is no larger than 48 bytes. With the modern standard of 24-bit color, a 16-color palette will be exactly 48 bytes. If all the attributes are acceptable, we continue to load the pixel data into a 2-dimensional array of color indexes, using the load method on that image object. Next, we need to determine how many rows of attributes we are going to need for this bitmap. We start by just dividing the height of the bitmap by 8, which will be the correct value if both the starting line and the height are evenly divisible by 8. If the starting line is not, we add 1 to the number of rows. If the height isn't, we add 1 if the sum of the height and the starting line is also not divisible by 8. Now that we have the correct row count, we can create an array of arrays that's sized to define 32 attributes for each row. Then we need to do some calculations to determine the size of the bitmap binary that we'll need to load into screen RAM. Depending on the starting line and the height, the lines of this image may not be in a contiguous section of screen RAM, requiring some empty patches in the middle. For the sake of simplicity, the image we are loading for this example is 64 pixels high and will be starting at line 64, which means that there will be no gaps within the binary, and loading this bitmap in won't overwrite any other pixels that we may want to preserve. The unfortunate truth is that there aren't many large swaths of screen RAM that will let you do this, so generally you want to either load a full screen image or do the partial screen load first and then add in additional graphics and text afterwards, or split the bitmap up into sections that can be loaded contiguously without overriding other lines or requiring any gaps. With these calculations out of the way for every line of the image, we are ready to define the starting row of attribute data and create another array of arrays that's properly sized for our bitmap. We then use some nested for loops to figure out what the bitmaps and attributes are going to be by analyzing each pixel. Luckily, we are doing this on a modern computer, and it can run through the whole thing almost instantaneously. Mainly, we need to make sure that the image will have the right attributes and that the lines of pixels are in the right order. Once we get through that analysis, we need to convert our bitmap array of arrays into a one-dimensional byte array. We need to consolidate groups of 8 ones and zeros into single bytes and place them into the byte array in the order that they need to be loaded into screen RAM. With the byte array completely encoded, we can write that out to a file named bitmap.bin. Then we take the attribute array and unroll that into a one-dimensional byte array as well. But for this, we already have the properly encoded bytes, so we don't need a third nested loop to do that. Then we write that out to colors.bin, and we're done. Now we have a script that is completely reusable for any time that we want to make a PNG into loadable bitmap and attribute files for a spectrum. So let's get back to that assembly code. Now we can see again how we were loading those binary files and making sure we have a label for the start of each of them. This will just put the data into regular user RAM, not screen RAM. This is something you will need to do fairly often with graphics data, as you will need to stage it somewhere in RAM so that it's readily available to copy to screen RAM for rendering when it's needed. Now we just need to define a few more constants to specify where this bitmap is going to be loaded. Line 64 in the screen RAM starts at hex address 4800, and we anticipate that this bitmap binary will be 2 kilobytes in total size. Then the attributes will need to start at row 8, so we calculate that address by multiplying the row number by 32, and adding that to the base address of the attribute RAM. The size of the attribute data should always be an eighth of the corresponding bitmap size, as it takes 8 bytes of bitmap data to define one tile with a single byte of attribute data. Next, we define one more section of the display area as the footer, which we will use for doing some programmatic bitmap drawing. Our last constant is for the start of UDG RAM, which is all the way down at hex FF58. Now we are finally ready to start our code. First, we want to make sure the default interrupts are happening, so we explicitly put the Z80 in interrupt mode 1 and enable maskable interrupts. This will ensure that the print routines are working, like the first one we call CL all to clear the display area and make it all the same color paper and no ink. Before we print the banner we defined earlier, we need to load up the UDGs with our custom bitmaps. An LDIR is the fastest way to do this. So we put the starting address of our first custom bitmap into HL, the start of UDG RAM into DE, and then the total size of our custom UDG bitmaps into BC and let it run. After the LDIR is done, we're ready to print the banner, so we first initialize our loop by putting the starting address of the banner string in HL. For each iteration, we load the next character code into A. If it's the stop code, we jump out of the loop. Note that we use a relative jump in this case, as this jump won't be taken until the last iteration, so this will be faster than an absolute jump. If it wasn't stop, we continue on to print the code using the RST10 ROM routine, increment our banner string pointer, and go back to the top of the loop. Once we get to that stop code, we jump ahead to load bitmap, where we copy the bitmap binary from where we included it in the program RAM into the actual screen RAM. Again, we do an LDIR and put the original address of the bitmap into HL, the target screen RAM address we defined earlier into DE, and the size of our bitmap into BC. Then we load the attributes we included with one more LDIR with the original address in HL, the target attribute RAM address we defined in DE, and the size of the attribute data we're loading into BC. Now we have all of our static graphics fully loaded and displayed. At this point, we want to start our loop for drawing dynamic bitmap graphics in the footer. What we're going to do in our footer is to continually flip all the bits in each byte of that section of bitmap screen RAM, doing one byte at a time in sequential order. We want to flip a single byte in each frame so that we can clearly see the line interleaving as the bitmap fills up, and then empties out again over and over. We're going to use the B register to hold the byte value we are going to write in each iteration of our loop. And since we cleared the display area earlier, we want to start by setting all the bits, so we load in hex FF. The loop starts with a halt instruction, which will wait for the next interrupt until continuing execution. This should happen at the beginning of the next video frame, so this loop should wake up and run 50 times a second, as that is the PAL TV scan rate. We copy the current byte value from B into screen RAM at the address in HL, and then increment HL to the address for the next iteration. Before looping back, we check to see that we haven't incremented past the end of the bitmap screen RAM and into the attribute segment. Luckily, we can quickly check this by seeing if bit 3 is set in H. No bitmap address in our footer will have that bit set, but the first byte of attribute RAM will, so once we hit that point, instead of going back to the top of the loop, we want to flip the bit pattern we're writing and go back to the top of the footer to start flipping the whole thing. We invert the value in B by first loading it into A, and then doing an exclusive OR with hex FF, which will flip all the bits, and then load the new value back into B. Then we finally go back to the top of the loop and wait for the next frame to start flipping all the footer bits all over again. That's all we have for the code, as this last loop will be infinite. So all that's left to do is have the assembler generate a snapshot named graphics.sna. And to do this, we have a build script. Before we can compile the assembly code, we need to generate the binaries that we are including. First, we make sure the pillow library is installed for Python. Then we run the Python script we wrote, passing in the PNG we exported from GIMP and specifying a starting line of 64. We omit the starting column argument, so it will default to 0. What this script call will do is effectively take this PNG, convert it to a 1-bit bitmap, and then interleave the lines based on the specified starting line and how it would need to be loaded into screen RAM. This is what bitmap.bin would look like if you tried reopening it in GIMP as a raw bitmap. But the Spectrum will interleave the lines correctly and apply the attributes that are generated in colors.bin when they are loaded into screen RAM. We then call sjasm plus with the LST option to generate a machine code listing and then pass it the name of our assembly file, graphics.asm. Now let's go to the terminal and run it. We run build.sh and then do a directory listing and see that the graphics.sna snapshot file is there. So let's load it into the emulator. We're using Fuse again, so we hit F3 and select graphics.sna and let it run. Now we can see that our static graphics load very quickly, and our dynamic graphics are often running, flipping all the bits in the footer 1 byte per frame. Now you can see the interleaving pattern that the Spectrum bitmap screen RAM uses, which is a bit unusual, but it can make certain things a bit easier and/or faster to code. We'll see some of those cases in later episodes, when we get into how to use these different graphics methods to create a game with virtual tiles, backgrounds, and even sprites, all with very minimal hardware support from the Spectrum, leaving most of the work for the Z80. Until then, I highly encourage you to play around with this example program and try creating your own graphics. In the linked GitHub repo, you'll find not only this code, but all of the code examples for each lesson, and all of the slides presented in this series. In the README, you'll also find links to some additional materials that can help explain what's going on, and provide some needed background in case your programming experience is a bit limited. Please subscribe to my channel and click the bell to be notified when the next episode comes out. And please like this video if you learned anything, and let YouTube know that you want to see more tutorials like this. If you can't wait for the next episode to go public, join our Patreon community and see my videos ad-free as soon as they are uploaded, just like the people you see here. Thanks for watching, and I hope to see you again soon. Bye-bye.